evening, students. In the last lecture, we saw about power supplies, the block diagram of a power supply, the components used in the power supplies. So with that, we got to know that rectifier is one of the most important component of the power supply, and we saw the construction and working of a half-wave rectifier with and without a smoothing capacitor, okay, with its waveforms and everything. So at the end of the previous video, I had asked a question regarding the half-wave rectification ripple factor. So I couldn't get the response from anyone. So please answer for the questions asked so that the concepts are clear. And also, if any questions from your side as well, please post it in the comments so that we can have a better understanding of the topics. Okay. So coming to today's lecture, today in power supplies we will be going for full wave rectifiers. So full wave rectifiers meaning the rectifier circuits, the work for both the positive and negative half cycles, okay, hence it's a full wave rectifier. So in these rectifiers we have two major categories: biphase rectifiers and bridge rectifier. Okay, so today now we will be seeing on biphase rectifiers. So here in figure 8 you can see the basic circuit of biphase rectifier. Okay, so here we have a step down transformer connected to the main supply of a 240 volts, and in the secondary winding, of the transformer, we can see that the winding has been split in the center, okay, and we get 12 volts for the first half of the winding and 12 volts for the second half of the winding. Okay, so but yes, the secondary voltage is considered to be 12 volts, not 24 volts. It is not the sum but the individual voltage. Okay, so this kind of transformer, we know that it's called as a center tapped transformer. Okay, so here we can see that we have two diodes D1 and D2, okay, connected at the extreme sides, okay, and then in the center we have a resistor connected to the point A, okay, through D1. So coming to the working of the biphase rectifier. So during the positive half cycle, when the positive half cycle comes at the primary winding, in the secondary winding, point A becomes positive, okay, and point B negative, and at the same time the point B goes for a positive and the point C the negative. Okay, so here we can see, so in this positive half cycle, diode D1 conducts, okay, and D2 does not conduct. When the negative half cycle appears at the primary winding, so we have point A negative and then point B positive, okay, and then again point B goes for a negative and point C positive. Okay, so we can and in this cycle diode D1, it does not conduct, okay, and D2 conducts, okay, giving us a voltage at the RL. So here in figure 2, in figure 3, okay, so this is for the positive half cycle, and this is for the negative half cycle. Okay. So as we saw just now, so in the positive half cycle, point A is positive and point B negative. At the same time, the secondary winding becomes the positive, and then the last one negative. Okay. So since we have a positive potential at point A, diode D1 conducts, and hence this diode D1 has been replaced by a closed switch. Okay. And diode D2, since for diode D2 we have negative potential, hence this does not conduct, it's a reverse biased diode, and hence an open switch, it is not conducting. Okay. So because of the switches now, we can analyze the flow of the current, that is from the positive terminal of the secondary winding, okay, and then through RL, and then back to the negative terminal of the secondary winding. Okay, so this is for the positive half cycle, and then when the negative cycle appears, we have point A as negative, point B positive, and then again point B goes for a negative and point C positive. Okay, and here now we have diode D2 conducting and D1 non-conducting. Hence D2 is a closed switch and D1 is an open switch. So the flow of the current, we can see that it starts from point C, okay, it starts from point C and then goes here, okay, through the intersection, and then back up to here. Since we have a open switch here, current does not go there, it comes here, goes through RL, okay, and then back to the negative terminal of the winding. So this would be your current path for the negative half cycle, giving us a voltage drop across RL. Okay, so this would be RL. Okay, now this is the entire working of the biphase rectifier circuit. Okay, so what would be the next version of the biphase rectifier circuit? It's the same as we saw in the half wave rectifier, that is introducing a smoothing capacitor or smoothing filter. Okay, and this smoothing filter, it is denoted by C1, and the work, it works as accordingly we saw in the half wave rectifier circuit. Yeah. So if you remember, for the half wave rectifier circuits, we calculated a V peak or rather the peak voltage, correct, for the RMS. And what was the value? The value was an exact equal to 16.9 something, which we approximated it to be 17 volts. Correct? It is only if your Vs, that is secondary voltage, is 12 volts. Considering the secondary voltage to be 12 volts, we saw that the peak voltage in the circuit is 17 volts. So what would be the voltage drop across? Voltage drop across D1 and D2. Okay. What would this be? This would be equal to 16.3 volts, considering 0.7 volts as the threshold voltage of the diode. Okay. So considering all this, so during the positive half cycle, capacitor C1 charges to the peak voltage C1. Okay, peak voltage, okay, that is 17 volts in the positive half cycle completely as soon as you get the secondary voltage. But the same when it goes for the negative half cycle, again it charges itself, okay, because we have a potential always. Only if we do not have a potential here across RL, then you might see a drop in the voltage across capacitor, okay, and that drop will lead to the discharge of the capacitor, okay, and it's a longer time because of the higher value of load resistor RL. So next we'll be going to the bridge rectifiers, which is one of the second category of our full wave rectifier circuits. Okay, so here we have on the board we have three different circuits. As of now, let's ignore figure 2 and 3 and come to figure 1. Okay, so the combination of diodes, your D1, D2, D3 and D4, here we call this configuration as the bridge configuration. Okay, so the positive, the top terminal and the bottom terminal, they are connected to the supply mains, okay, and the rightmost, the positive, this is the positive terminal and the left is the negative terminal of the configuration. Okay, so using this bridge configuration, we come up with the bridge rectifier circuit, wherein we have a transformer, the bridge configuration, and then a load resistor RL. Okay, so again we assume the input for the rectifier to be a 240 volts supply, okay, which gives us a secondary voltage of 12 volts from the secondary value. Okay, so during the positive half cycle, diodes D1 and D2 conduct and D3 and D4 are non-conducting, giving us a voltage across RL. Okay, and then next we have the negative half cycle, in which diodes D3 and D4 conduct and D1 and D2 do not conduct. Okay, and even at this negative half cycle, again we have a voltage drop across R. Okay, so coming to the current flow of the circuit, this we can see in figure 2 and figure 3. So figure 2, it's for the positive half cycle. Okay, and figure 3 for the negative half cycle. Okay. So in positive half cycle, the point A becomes positive when compared to the point B. Okay, which are the points for the secondary winding. Okay, so when we have a positive half cycle at the primary winding, current flows from the positive terminal of the secondary winding. Okay, and then since we have D1 and D2 conducting, so these diodes D1 and D2 are replaced by closed switches and D3 and D4 by open switches. Okay, so the current flows through D1 and then through the load resistor RL, and then coming back to the negative terminal of the bridge configuration, and then through D2 and then back to the negative terminal of the secondary winding. Okay, so here you can see we have identified the current direction through arrow marks, and I have denoted current here as the small letter I. Okay, so this is current in case of both the diagrams. Small I, it stands for the current. As we know that current is denoted by either capital I or small i's. Normally capital I when it comes to DC and small I AC. Okay, AC or even the small signal models, okay, which we will be studying in some other subjects in the future. Okay, so after this we have a voltage drop across RL giving us some waveform. Okay, and in the negative half cycle we have point A negative and point B positive, and hence D1 and D2 are open and D3 and D4 become closed switches. Okay, so in this case the current starts from the positive terminal of the secondary winding, that is the point B. Okay, point B, and then through D3 and then through RL back to the negative terminal of the bridge configuration, and then through D4 and then back to the negative terminal of the secondary winding. Okay, so this would be the current flow for both the bridge rectifier circuits. So if 12 volts is considered to be the secondary voltage, then obvious it is the RMS voltage. Okay, and hence again we have here peak voltage to be considered as 17 volts. Okay, in case of the same as in case of the previous circuits. Hence, if you introduce the capacitor, if you introduce a capacitor into this circuit, which would be the smoothing capacitor, okay, so that appears at the positive and negative terminal here. Okay, since I have a bit less space here, I am doing it. Else if you want me to, if you want a better picture, just erase this part. Here we will smoothing capacitor C1, the resistor RL, and again here we had D3. Okay, so in order to remove some unwanted signals from the circuit and for the smoothing of waveforms, we have capacitor C1 introduced, okay, which would be the smoothing capacitor, and the charging time, again it would take the product of the forward resistance, okay, forward resistances multiplied with capacitance C1, okay, and the discharging the product of RL and C1, okay, and the peak voltage for this capacitor C1, that is the maximum voltage it can be charged at, it would be again, so the maximum voltage at which C1 can be charged is 17 volts minus 0.7 volts, which would be again 16.3 volts, as we saw in our previous cases of biphase rectifiers and half wave rectifiers. Okay, so here again we have a longer discharging time, okay, longer discharging time and shorter charging time, okay, for this capacitor C1. So now let's see some voltage waveforms, okay, for the full wave rectifier circuits. So we have the waveforms for the full wave rectifiers on the board. Here I have the voltage for secondary voltage across the T1, and then voltage across the load resistor RL without the smoothing capacitor C1, and voltage across the load resistor with smoothing capacitor. So here the secondary voltage, we can see that it's a sinusoidal waveform having a peak voltage of 17 volts, which we had calculated during the construction of full wave rectifier circuits, both biphase and bridge. And then the voltage across load capacitor, it would be the 16.3 volts, okay, because of the drop in the voltage drop across the diode. And we can see that we have the complete waveforms for both positive and negative half cycles, okay, compared to the half wave rectifier which we have seen in the previous video. And the same with capacitor C1, we get ripples generated, okay, in the output voltage when we have smoothing capacitor. So if anybody can comment the ripple factors for all the three circuits which we have come across, that is the half wave rectifier, the biphase rectifier and the bridge rectifier. If anybody can comment the ripple factors for all the three circuits, it would be a very good response from you guys. Okay, so this marks the end of our rectifier circuits. Next we will be seeing on regulators. Okay, so thank you. Like, comment, share and subscribe to the channel. Thank you.